Connecting to audio. Oh, hello. Oh, and we got two more people coming in.
Fantastic.
Daniel and Terrell.
But I need not. Gallery view. Okay.
Yeah, I don't know how to use Zoom. So.
Hello.
Oh, hello. Hey, Daniel.
Hey, how's it going?
Oh, it's going well. How are you?
I'm doing well. Good to see everyone.
Yeah, totally.
Good to see any people at all.
Carrot juice here. Got my whiteboard.
Oh, beautiful. Beautiful.
You might want to, wow,
Yeah,
you might want to angle the screen just a little lower.
A little down. Yeah.
True. Oh, there it is. I see. My
yeah,
there you go. Perfect.
Thing. That's pretty good. Yeah. And make sure to write kind of big.
Yeah.
Yeah, it's a little difficult to see. Although, I could probably expand this view.
So, can you guys see my screen?
Yes. Yep.
Okay. So, because I have all these nice notes.
It all looks good. Yeah.
It'll be if the whiteboard fails, we'll have this going on here.
Yeah.
I'm also going to pin your video. There you go. That'll work.
Hello, Terrell. Nice to meet you. I don't know if we...
Hey, guys. Thanks for allowing me to drop in and meet you all. I'm in Harrisburg, Pennsylvania, for what that's worth.
Nice.
But I did live in Brooklyn for a few years, so...
Well, same here. I'm in New Jersey right now.
Ah.
So,
Where are you, Matt?
I'm in New Jersey.
Oh, nice. What part of New Jersey?
In South Jersey, Morristown, kind of near Philadelphia.
Yeah. No, I know. I actually have two friends right now quarantining in South Jersey. So,
nice.
Yeah.
Cool. Yeah, it's just kind of a rainy day. Is it raining? Where?
Yeah, it's wet here.
Yeah.
Oh, is that Tim? On here?
Hello?
Oh, hello. I hear you, but I don't see you.
I've gone dark today.
Okay.
It's a choice.
Oh, man.
Speculating about who would decide to go video, who would go. Well, because I'm recording this with your guys' permission. I was going to put it on YouTube. So I don't know exactly how Zoom manages the different videos, when it puts the video together.
Actually, I'm finding that interesting in the 30 or 40 Zoom meetings you got during the week. Each group seems to have a culture. It's either Zoom or no Zoom. Sorry, video or no video.
Yeah.
Right.
Sure.
And if 90% are on video, they blast you, turn your video off.
Exactly.
And
yeah,
it's a whole new way of dividing the world. Are you video or not on Zoom?
Yeah, right.
There's a lot of peer pressure to turn your video on when everyone else is videoing.
I mean, the technology is pretty good. You guys are all coming in pretty clear,
It's impressive.
Yeah, it does look really nice.
So I guess let's give it a couple more minutes.
Sure.
I think Marty was going to show up.
How are you, Tim? Are you in Brooklyn still?
Yes. No, in Queens.
Okay. Nice.
In Queens, yes. Since the last meetup, I've moved out of Brooklyn.
Wow.
Where are you, in Baltimore?
I'm in Cherry Hill, not very far from Matt, actually, at the moment.
Nice.
Well, is there any interesting physics stuff that you guys have been thinking about? It's been so long, what thinking about?
More casual stuff. I was reading the simulation hypothesis. I don't know if you've heard of that. That's a good one. That's an interesting one. For me, I don't know if anyone knows or remembers from older meetings. I'm an animator working in the cybersecurity field, and so for me, thinking about quantum mechanics a lot of times equates to thinking about how computers render things out. And that's been like that for about 20 years for me. So reading this is somewhat seems somewhat validating to that thought process. And it's just really, whether proven true or not, I don't know how it will be proven true, but it's an enjoyable read, even even just as a hypothesis. So it's a good one.
Yeah, I'd like to meet the animator that's made this simulation possible.
Yeah.
What tool are they using? What is it, Unify, or what's the name of one of those animation tools?
Oh, there's so many. I use After Effects, but 3D stuff is a lot of 3D Cinema Max, a lot of Maya, Cinema 4D. There's a lot of programs that you can use.
Hey, Marty. Hello. I don't know.
We haven't.
I don't know if he can hear or see us.
His audio is not yet connected.
Yeah,
I think.
Classic.
Or he's intentionally muted. Either one.
He is muted right now. I see that.
But yeah, it does seem like, if building, computer simulations full of people and worlds is possible, then it does seem likely that we're in one. But
yeah, the real question is
whether it's a classical or a quantum simulation, maybe.
Right.
Who
The
knows?
real question is, are we plugged into the simulation, or are we part of the simulation? I guess that would be the real question. Are we AI inside the simulation, or are we somehow plugged into it?
I was watching these lectures by, and I mentioned this guy, not necessarily to endorse his work, but I find him very interesting. Eric Weinstein.
Yes, a friend of mine just recommended him on, I think it was Joe Rogan podcast.
Yeah.
He's talking about escaping.
What happens when mankind learns its own source code,
Exactly. Yeah, I was just listening to that the other day, actually. It's interesting. It's kind of funny. He talks about escaping the simulation, which is to me, that's a ridiculous statement, but who knows?
That's the right goal to have.
Yeah, I kind of agree with that. It seems like a ridiculous goal to have, to escape the simulation, because what lies beyond the simulation that's actually even fathomable to us? It's just seems ridiculous.
What I do like about Eric Weinstein is the way that he seamlessly weaves together this sort of socio-political analysis
all the time. Yep.
Existential angst with his physics.
Right. Right. That's such a good way to describe it. He's very angsty. He is very angsty.
I like him a lot.
Yeah. He speaks very as a matter of fact. Everything he says, this is how it is. That's how he speaks. So it's pretty enjoyable at times.
Oh, we got an Andre incoming. Nice. Well, I guess we can start in a couple minutes. We're getting, let's see, can I send little messages, chats to you guys?
Yeah, the bottom bar just says chat.
Mm-hmm.
You can send it to everyone or anyone in specific.
Start a new chat.
Actually, you guys got me thinking now. So you got a simulation, right? And it'd be layers of the onion. So layers of the onion, just like I think it was Daniel was in cybersecurity, right?
Yeah.
So imagine you're a bit in a laptop, right? And then you've got the machine language surrounding that. Then you got another layer of assembler, right? Then you got another layer of your programming language, let's say COBOL or Python, right?
Mm-hmm.
So how do you think that bit feels?
Yeah, lonely, I would say.
Being manipulated by the outer layers of the onion that it has no idea exists.
So
where does that onion end?
Yeah. Well, that's the whole thing. How would you ever know if it ever did end? It's just like infinite regression, right? It's just it keeps going forever. Anyone watching Devs by any chance? Because that touches on that idea.
Wait, what is it?
Devs, D-E-V-S.
Oh, Devs. Yeah,
Devs.
No, I haven't
That's
seen
a show about software developers.
It's a show about a quantum computer that can do things that probably a quantum computer can't do at this. But whatever, it's enjoyable. Yeah. It's fun to watch. But yeah, they do.
Scott Aronson had a post about it where he was reviewing it. He liked the show, but he was like, yeah, it's not really about quantum. No. You consider this an example of cultural appropriation.
Exactly. It's kind of like,
Just take
ideas of what the microwave is capable of, 50 years ago. Can you give yourself superpowers by starting your microwave and tearing the door off your microwave? It touches on things that people don't understand and then
wordcounter.com.
spins them nicely. But
That would.
So I sent you guys a GitHub link in the chat.
oh, okay.
And so like, if you want to follow along with the notes, these are like these Python notebooks, which I think if you click on them in GitHub, it'll like render all the LaTeX and everything.
Wow.
Yeah,
Cool.
it looks nice.
This will be
It looks very nice.
what we work off of here. Very time consuming.
Absolutely.
But you feel like, it was Donald Knuth, right? Who like came up with LaTeX, is that right?
Yeah.
You feel like you're hanging out with him. It's just so funny, like, to make like a parenthesis big, you're like /big parenthesis.
Yeah.
Like all of it's just very funny. It's sort of like seemingly unsystematic, and yet you can really go kind of quickly.
Control it very finely. Yeah.
Anyway. Well, okay, so let's get started a little bit. So, wait, when you can see my screen, can you see like all the Zoom windows?
No.
No, you only see the screen that you have selected.
Zoom is cool, so it just knocks those. Okay, great. So you see this paper here, Quantum Gravity in the Lab.
Yes.
Teleportation by size and traversable wormhole. So this is basically like what we're going to be going on. Like I've taken this paper and I have like kind of broken it down at like a more or less elementary level. Like it's, is going to presume that, you've seen like a little bit of this stuff before, qubits and linear transformations and stuff. But like I try to make it like more or less self-contained so that like if you have questions, it'll be like, nice moments where that can happen. This paper came out back in November, and it's got some pretty illustrious people on it. And I saw it as a kind of like call to arms, in the sense that it's not like presenting deeply new results, but it's kind of like an overview of like a lot of work that's been done in this particular field, and particularly shows that you can come up with these simple models of wormholes with just like some qubits, which kind of is a nice way of formulating it because it frees you up from worrying about like more complicated things. In the future, in a future like meeting, we can talk about some more sophisticated models like the SYK model and other things. But this is a great place to start because it is familiar to anyone who knows a thing or two about quantum computation. So I just thought, before we get into the meat of it, I would just pull out a couple things here. So here, I'll read this little part. We're going to focus on a surprising communication phenomenon. We'll examine a particular entangled state, one that could actually be made in an atomic physics lab, and consider the fate of a message inserted into the system in a certain way. Since the system is chaotic, the message is soon dissolved amongst the constituent parts of the system. The surprise is what happens next. After a period in which the message seems thoroughly scrambled with the rest of the state, the message then abruptly unscrambles and recoheres at a point far away from where it was originally inserted. The signal has unexpectedly refocused without it being at all obvious what it was that acted as the lens. If we imagine the initial entangled quantum state consists of two entangled black holes, then there's a natural explanation for why the message reappears. They travel through a wormhole connecting the two black holes. I'll go into this a little bit more. Here's the sort of quantum circuit for it, and here's a sort of space-time diagram. So just to give you a sense of where we're going to go. Okay. Any questions so far? Like any concerns anyone has about wormholes? The people who work on this, there's many, many different approaches to quantum gravity. There's all the stuff coming purely out of string theory. You got your loop quantum gravity people. You got, 7,000 different ideas out there. One idea that, I kind of like, is this idea of like black hole complementarity. And, you know, in answer to the question, like what happens to the things that fall into a black hole? The answer is that, you know, whereas like suppose, you know, can you see this? Sort of, not really. You have a black hole, okay? And B is going into the black hole, and A is watching. What A is gonna see is B get ever closer to the event horizon of the black hole, ever more slowly, and look, kind of get smeared out over its surface. But B is just gonna pass through that event horizon like it's empty space. And the idea is that in the presence of a horizon, there's actually two different perspectives on the quantum, like the Hilbert space. And this is the idea of black hole complementarity, that there's two complementary pictures. If you stay outside the wormhole or the black hole, you see one thing. If you go in, you see another thing. And so this is why the idea of information scrambling is important, because we're gonna model the idea of like something descending into a black hole and eventually a wormhole in terms of thinking about like a qubit getting scrambled out over all of the degrees of freedom of the black hole. And the idea is that you see this, you know, space-time diagram here. You have a black hole on the left side, a black hole on the right side. You insert your message in the past. It goes off at the speed of light. It passes the left horizon, and now it's like in the black hole. And if you don't do anything else, it eventually hits the singularity at the top of the diagram. What we're gonna do is something that's kind of like inspired by quantum teleportation. We're gonna introduce a coupling that you see on the right diagram. And geometrically, this coupling is gonna, and it sounds great.
It is now, man.
Oh.
I'm gonna mute us for now. I don't want to interrupt it.
Oh.
Hello. We have joined.
Nice. Welcome.
It's
We're
nice to
just
see
getting
you.
started.
Awesome.
Giving a very broad and confusing overview of what we're about to talk about. So in this left picture, you have just two entangled black holes without a coupling, and they're not traversable. Something falls in, doesn't come out. But on the right, we introduce a coupling that makes wormholes traversable. And you can think about it, and this sounds crazy, like a negative energy shock wave that translates the signal back in time to a place where it's now outside of the horizon on the right, and so it can emerge. So anyway, let's get into it. So like, let's not dwell on.
Can I ask a question, Matthew?
Yeah.
Michael.
Who is that, Marty? Is that you, Marty?
No, Michael.
Oh, hi, Michael.
Who's this?
Oh, it's Richard Weiss. I'm Matthew's dad.
Oh, okay. Matthew, going back to the last frame, are they contending that you can send a message from outside of the left black hole and it will wind up outside of the right black hole? Because I noticed that Susskind is one of the authors of this paper, but that's not what he contends in his YouTubes. He says you can never send a message. Once something falls into a black hole, even if it's entangled with another black hole, it's not going to wind up outside of the other black hole. But is this what they're contending?
But they're contending, yeah. So in the last couple of years,
how does it get out of the entangled black hole? How does it get out of the entangled black hole? Nothing can get out of a black hole.
That's what you think, but you know, if it's understood in a properly quantum mechanical manner, you can show that the wormhole analysis makes sense in just the same way as quantum teleportation makes sense.
Yeah,
so
but you can send the signal from one black hole to the other, from one black hole to the interior of the other black hole, but you can't get out of the other black hole because it would have to be traveling faster than the speed of light.
Yeah, well, so what we do is the black holes are entangled, but then we're gonna make the black holes interact. There's gonna be a coupling between the outsides of the two black holes. And that's what's gonna allow the wormhole to become. So it's not just like any two entangled black holes. The black holes have to be, so like in a more realistic example, like Juan Maldacena has some papers on this. It's like, you can imagine some kinds of, quantum fields that are like coupling, like the two black holes together because like they're close together in space or something. So yeah, it's not just like any old two entangled black holes. They have to interact in exactly the same way as in quantum teleportation. You can have two entangled particles and use them to kind of teleport one qubit from a place to a place. But in order to do it, you make a measurement and then you have to send a classical signal to your friend who has the other entangled qubit, and then they have to do like a correction. And so, that like requires some classical communication, which can only propagate at the speed of light.
So essentially what we're saying here is that we can send information faster than the speed of light through entangled black holes.
Well, no, because, the thing falls into the black hole, on the left black hole. And then, you have to do the coupling, and the coupling can only happen at, like less than the speed of light. So like it won't,
So then what's the point? Why do that?
If you, like in general, like, why, like I would say, yeah, like quantum teleportation's kind of like teleportation in Star Trek, but you sort of have to like prepare the portal beforehand. You can't just like beam down onto the surface willy-nilly to like some arbitrary place. But it's sort of profound in the sense that like something can like, move from place to place, like without like obviously, just like moving through like, the familiar space. Like something can like disappear here and like pop up over here, like without having, so.
Hey, Matt, can I ask a question real fast, just for clarification purposes? What type of black holes are we talking about in this scenario?
Black ones.
Very simplified ones.
Like just mass only black?
Yeah, like, look, no one has like the final word on black holes.
Well, there's only stationary, spinning, and charged. Mm-hmm. And as far as we know, charge don't exist. So it's got to be, this assumes a stationary black hole, but real black holes spin.
Sure. So, we're going to be literally modeling a black hole as like 7 qubits. Okay. So, it's not going to be, astrophysically accurate. There's other smarter people with the chops who are working on that problem. But this is something that I think if you have like a little programming experience, a little basic knowledge of like quantum computing, say, then you can do this on your laptop and play around with it. And we're actually at a point in the field where like that would be really helpful, because the idea is that we want to kind of explore this sort of like wide class of systems, and a lot of that's just gonna be trial and error, people exploring the kind of like computational landscape of things that give you interesting geometries in this very simple form.
Matthew, can you just say a little bit about that diagram on the left again? What is a left and right horizon? I guess I don't get that.
Right, so this is gonna be, it's a model of a two-sided like eternal black hole. So there's like a left black hole and a right black hole, and they're entangled, basically.
So are these the paths? That line labeled left horizon, what is it?
That's the event horizon of the left black hole.
So at one point they were both together? What is the fact that the left horizon and right horizon meet? Seems like that's an event. The way I read this, without those names on it, is that there's an event and that there's the light cone of things, of possible information from that event leaving that event. But I don't understand then putting the words on it, left and right horizon.
So it's like the upper triangle there is like the shared interior of like the two black holes. And, there's like an event horizon on the left and an event horizon on the right. But let's come back to this in a little bit. Is that okay?
These are Penrose diagrams, is that right?
Yeah. Because, you know, to really get, so the question is, like, we can talk all day about wormholes and how cool they are, but, you know, it's sort of like, what's the perspective from which it's sort of obvious that a wormhole could exist? You know what I mean? So I want to like motivate this, you know, using some sort of like elementary facts about entangled states. So we're gonna start off here, part 1, yanking. And I think I will not use the whiteboard as much because it is hard to see. So I have here, you know, the 2x2 identity matrix, and that's where we start, okay? Oh, actually, I want this one. You know, what's with that? Look here, on GitHub, all my column vectors have become row vectors.
Oh, yeah, it's the rendering of LaTeX is maybe a little flaky.
All right.
Is that yanking a noun or a verb?
Yanking.
Is that some guy yanking? Or is it a city in China, Yanking?
Oh.
So how did you correct the vector to?
Oh, I just opened it up in the actual Python, like Jupyter notebook instead of
Okay.
rendering. Okay, so basic fact about the identity matrix is that you multiply it by any vector and it just gives you back that same vector. Trivial. But everything begins with a triviality, you know. Let's unfurl the 2x2 identity matrix into a 4x1 vector. What have I done? I've just taken the first row and then the second row and I stuck them together. 1, 0, 0, 1, 1, 0, 0, 1, okay? So how can we interpret this little 4-dimensional vector, okay? So we're gonna review something which is the tensor product, which is how systems combine in quantum mechanics. So we have 2 qubits A and B, and they're each 2-dimensional systems. And so they can be written as A can be written as a linear combination of an upstate and a downstate, where A and B are complex numbers, and where the upstates and downstates are just defined as these like little basis vectors here. We'll go a little bit more into the geometry of that later, but okay, so we have qubit A and qubit B. We can tensor them together. And what I have here is that the, you know, A tensor B lives in this tensor product space. It's 4-dimensional, and the basis vectors are labeled by, you know, both qubit A and B are in the upstate, qubit A is in the up, B is in the down, and so forth, okay? And what that means is that we can interpret this 4-dimensional little state here as one of the maximally entangled states of 2 qubits. If you look at it, this is the state where either both qubits are up or both qubits are down if you measure along the z axis. Again, we're going to come back to that. So this is a state where, you know, when you go to measure either A or B in the z axis, it's going to give you up or down with probability 1/2, but the 2 qubits are always going to agree. Here's a little review of the bracket formalism that we're using. So, you know, we refer to a column vector as a ket, and a row vector is a bra, and we can turn a ket into a bra by just turning the vector on its side and complex conjugating its entries. And for, you know, remember, complex conjugation is just if you have some complex number x plus iy goes to x minus iy. And the point is that when you know, watch what happens. You know, if you have x plus iy, and then you multiply it by x minus iy, it goes to x squared plus y squared. And if we have, yx, we then have a triangle. If you have a triangle, then this is just the area of the square on the hypotenuse. And that gives you the probability. So in terms of the bra and the ket, we could define the inner product of 2 vectors, 2 quantum states. And it's written, that's why, you know, they call it the bracket formalism, because you put a bra next to a ket and you make a bracket, okay? And you see how you calculate it. You just go through each of the entries and in the two vectors, the bra and the ket, and you multiply them. So you have A conjugate times A plus B conjugate times B and so forth. We can do the opposite. That's the inner product. What about the outer product? We can have a ket times a bra. And here we see what we've done is, if you look at it, each row of this matrix is just ABCD, our row vector, times the first element in the bra. So, you know, along the first column, it goes like ABCD, and then you have the A conjugates and so forth. And so this pattern it's the outer product, also known as the tensor product. You can see here, I've written out, like, so if you wanted to tensor two up states, you would get that state. And the idea is that you look at the guy on the right, which is 1, 0, and you stick two copies of it on top of each other, and each copy is going to be multiplied by the coefficient of the first guy, or the component of the first guy. So what you have here is that, I'll write it out a little bit better, 1, 0, 1, 0, but then this one is multiplied by 1, and then this one is multiplied by 0, and so you get 1, 0, 0, 0. Okay. Just a review. We can define the expectation value of operators. In other words, like the average value of that operator. And this is the thing that is going to be like, you know, the most classical part of your quantum system, in the sense that, you know, in the limit, like this is like where you're going to get your classical position, momentum, or whatever. It's like the average. Like all the things that we know and love from from classical mechanics turn out to be these like sort of quantum mechanical averages. So you just wedge an operator between a bra and a ket, and you can form projectors, which are the outer products of these little vectors, and you can use them to find the probability of, you know, that particular state, that a given state will collapse into the state represented by the projector. Now, and again, if there's any questions, let me know. I'm going very quickly. I just want to get through this one part, you know, and open it up to questions, as I say. So it's really important when you're working with these vectors and matrices, like especially if you haven't done it a lot, to like, you got to get like a visual, like kind of kinesthetic feel for like how these things fit together. All right. So like, let's visualize the tensor product for a second. We have an operator, 2x2 operator, A, B, C, and D, okay? And we're gonna tensor it with the identity. And we're gonna do it two different ways. We're gonna do the operator tensor the identity, and the identity tensor the operator. And we're gonna look at the difference between them. And what you see is that if you do it from the left, you get this kind of pattern, you know, A, 0, B, 0, A, 0, B, 0, you know, whatever. And then if you do it in the, on the right, you see it, you know, you get kind of like a block and then another block, okay? Does that make sense to everyone how you get this result? If you look at it, if you divide this matrix up, wait, you can see my, my mouse cursor. So if you take this matrix and divide it like this, see, into these 4 quadrants, you notice that each of the quadrant is just the identity matrix times A. The identity matrix times B, the identity matrix times C, the identity matrix times D. And similarly, on the right-hand side, you see that each one of these 4 quadrants is just ABC, but multiplied by either 1 up here, or 0, or 0, or 1, okay? So that's how the tensor product works. When you tensor two things, for every state of the one system, you get an entire copy of the other system. And that's really important because like that's pretty much how it's like why all the magic happens, okay? So just a little example, just to run through, make sure we understand about entangled states. So suppose we start off in a maximally entangled state and we act with an up projector on the left side. You can see here, I've taken the up projector and I've tensored it with the identity. And then I've created my little entangled state. And I do the multiplication and you see you get the vector that corresponds to both are up. So if I measure that the left qubit is in the up state, then it turns out both of them are in the up state. Similarly, with the down projector, both of them end up in the down state, okay? And for this particular state, the maximally entangled state, the same is true if you do it on the right side. So we can project the right qubit into the up state, and then they're both up. And you can project the right qubit into the down state, and they're both down. You can get the probability in this way. You have, our states, which we've normalized, just probabilities have to sum to 1. And we've just wedged the Braun-Kent version of our maximally entangled state. And in the middle, we have the projector. And it gives us the probability, a half, as we claimed. Okay. All right, so now we're gonna do what we did before. Look at the difference between tensoring an operator with the identity from the left or the right. But now we're gonna consider the action of that operator on the maximally entangled state. So here we've denoted the maximally entangled state by 5+. So we consider the operator acting on the left, right? So we have here little A, B, C, D as our operator, tensored with the identity, so it acts on the left. And we act on our maximally entangled state. And behold, what do you get? You just get A, B, C, D. Isn't that interesting? So up here, we began with this thing. We started with the identity matrix. Then we unstrung it into a vector, 1, 0, 0, 1, 1, 0, 0, 1. Well, this is actually, a general principle here. If we take an operator on the left, multiplied by the maximally entangled state, the vector that you end up with is just that operator strung out as a vector, okay? This is gonna be a recurring theme. What about on the right? We could take an operator, tensor it with the identity on the left, so it acts only on the right side, and then we see what happens when we act on the maximally entangled state. And we see we get ACBD. So it's kind of like ABCD, but a little bit whatever. In fact, what it is, it's the transpose. So we can define the transpose of O. If O is ABCD, transpose is ACBD. And from that, we could reason that well, what if we acted with O transpose on the right side and acted on the maximally entangled state? Then we would just get ABCD like we did before. And so we come, and so this little—
Excuse me, Matthew, just a mathematical question. In general, does this, do similar patterns hold for higher rank matrices?
So yeah, so you can consider just any two Hilbert spaces of the same dimensionality and consider a maximally entangled state between them, yeah.
But I mean, let's say you have just in general an n by n matrix. Let's say a 10 by 10, and you string it out. Will you get
Yeah.
Or does this only work for 2 by 2s?
No, it works for any dimensionality. It's not dependent at all on the 2 by 2 cases. I just decided to go with the 2 by 2 case because
simple.
I need to excuse for that. Okay. So this equation here is going to be very fundamental for us. It says that an operator acting on the left on the maximally entangled state is indistinguishable from acting with the operator transposed on the right side of the maximally entangled state. So already we can see there's some cool stuff happening, okay, when we have a maximally entangled state. Stuff you do on the left and stuff you do on the right are not unrelated to each other because of the entanglement. So now, because the bracket formalism, we're going to employ it, is great, but it can get a little bit nauseating. I mean, as we were just saying, when the matrices are not 2 by 2 matrices. So we're gonna very quickly define the famous string diagram language, which makes all multilinear algebra calculations visually obvious and appealing. So we're gonna define first what we're gonna call the cup state. And the cup state is just the maximally entangled state. Okay, you already know that. The cap state, see, the cup is a U, the cap is a little upside down U. The cap state is just the maximally entangled state, but the bra version of it. We're gonna denote a wire by, or we're gonna denote the identity matrix by a wire. And the rules are, the rule is that if we have two, say, operators or states and they're next to each other, we're gonna tensor them. But if two things are on top of each other, we're gonna multiply them. Okay, well, we're gonna see how this works. And then finally, just for, you know, amusement's sake, I have here the swap operator. So this is gonna permute 2 qubits. Come back. All right, so now we come to the great thing, the yanking equation, hence yanking, okay? This is the yanking equation. And it's called the yanking equation because you imagine this like a piece of string, and you just grab both ends of it and you pull it, then you can see that that equation is true. Like it's certainly true for strings, okay? The question is it true for our quantum stuff? And we'll show that it is. So how do we interpret this diagram in terms of our linear algebra or vectors in our matrices? So the rule for translating a diagram like this into math is to slice it horizontally, figure out what has to be tensored together, do that for each layer, and then like multiply them from bottom to top. So what we have in the first layer is the identity, just a wire, tensored with the maximally entangled state with this cup. In the second layer, we have the cap state, which remember is the bra version of the maximally entangled state, tensored with the identity, tensored with a wire. And so this equation is just saying that if we take the identity tensored with the maximally entangled state, and then multiply it by the maximally entangled state tensored as the bra version of it, tensored with the identity, then that's just the identity. And, you know, you can check that that's actually true. And let's do it. Let's actually check it. So here we have the maximally entangled state. Here we have the identity. And then we have the identity, the maximally entangled state. If you multiply these out, you see, you know, you can, the tensor product thing works for any dimension. So you see that this long rectangle is made up of these little 2 by 2 blocks, right? Where each 2 by 2 block is an identity matrix, but each one is multiplied by the coefficient from this guy. And similarly here. And when you multiply these together, you just get the identity matrix. And so we've proved it. The yanking equation is true. Pretty cool. And moreover, you know, suppose we just had some random operator, like it wasn't the identity. Like in other words, imagine there was like an operator right here. Would this mean that we could just sort of slide the operator around this and like have it pop out over here? And it does. Here we have the maximally, the bra version of the maximally entangled state. We have the identity multiplied by some operator A, B, C, D times the maximally entangled state. We see it's just A, B, C, D. So now we can translate our interesting equation that we discovered earlier into these pictures. So we have an operator acting on the left on the maximally entangled state equals an operator, the transpose of an operator, the same operator, acting on the right on the maximally entangled state, where this is O transpose. And you see that this is really just saying that we can take O and we can slide it around the cup, and when it comes up on the other side, it's the transpose, it's upside down, which is in fact how things actually work, just geometrically with strings and crap. You know what I mean? Like, take a little shape and you're like, no, it's upside down. So we can, and incidentally, it's just for typesetting reasons, I could have made this little square, you know, asymmetrical so you could see that, but instead I just put OT.
Hey, Matthew, can you make that full screen?
Yeah, maybe we
Yeah,
A little bigger.
Yeah, you'll see it better if you make it full screen. Thanks.
indeed. Let me rearrange these windows a little bit. Okie dokie. So we can track an operator as we, sort of slide it around this yanking equation. It comes up, it goes over the cap, then it goes the transpose of itself, but then it goes around the cup, and then it comes back to itself. Nice. And then finally, to close out like our just sort of overview, refresher of various linear algebra and diagram facts, one useful thing that the string diagrams, many things become transparent once you put things in this form. So for example, it can be confusing at first when you first learn like how to take a partial trace. In other words, if you have a tensor product of quantum systems, it's in a pure state, you can get a mixed state, in other words, a density matrix for each of the subsystems. And everything about an individual subsystem that can be predicted, locally, all that information can be predicted from the density matrix. So the question is, how do you get that? And an easy way to do it is this. So suppose we have, we'll do it for the maximally entangled state. So first we create an overall density matrix for both A and B. And the rule for if you just have a pure state and you want to get a density matrix is to just take the outer product of the bra and the ket. So we have here the bra times, ket times bra. And then if we want to trace over one of the systems, it just means sum over one of the subsystems. And so what we can do is we can represent that density matrix of both systems as this little box. And then we're going to do this trace over B, which we have denoted like this. So, I mean, if you write it out, what this is the identity tensor, the cup, times this density matrix tensor, the identity, times the identity tensored with the cap. And similar, so this would give you the partial state of A by tracing over B. And similarly, you can get the partial state of B by tracing over A. So then, here's a little numerical calculation that like in fact works. So here's some Python code. Here's the identity, there's the cup, here's the cap, here's the overall density matrix, here's precisely that calculation that I did up here for each row A and row B. And then, I recommend using Qtip, which is like a Python library for quantum stuff. And they have a built-in function that lets you take the p-trace, and you see that it gives exactly the right answer because it printed true. So there you go. Okay, so that's part one. Any questions? I know that was fast, but
just a technical question. How do we get a copy of that?
Oh, yes. Yeah, Marty, let me, I had a little GitHub link that I sent out to the chat. So I put this on GitHub. I will, after the meeting, make a README file because it can be a little confusing. So you can read it on GitHub just fine. If you want to run it in a Jupyter notebook, then you're gonna have to install that. You're gonna have to install Qtip. You're gonna have to install VPython, and you're gonna have to install an extension so that VPython can work with Jupyter Notebook. VPython, we will see, we haven't used it yet, is a very simple graphics library for drawing cool 3D pictures.
Matthew, are all of your visuals at that link? The paper, the paper you showed, and whatever else you're going to show?
Is each section of the length that it took to go through the yanking? Is that what you're asking?
No, the link that you gave.
Oh, the link. I thought you said the length.
No, the link. Are all your visuals on that link?
Yeah, they are. Yeah,
that totally. Paper and
yes, the paper, the reference paper, all of the notes, all of the images. Yeah, it's all there. All the code.
Right. Thank you.
Cool. So should we move on a little bit? Should we talk about quantum teleportation? I think we should. There's never enough, you know. Anyway. So you can think about quantum teleportation as kind of like our yanking equation, but there's a measurement. Okay. So you can see here, I've taken the yanking equation and okay. We have the identity coming in, you know, some state maybe is coming this wire. We have the maximally entangled state. But instead of the cap on the left, we make a measurement, okay? And then we're gonna send these little dotted lines represent sending the result of that measurement, which is just some classical, this is a number, to someone else. So, okay, I should say. The simplest way of talking about quantum teleportation is you have 3 qubits, all right? A is the one that we're gonna teleport, and B and C are in this cup state, okay? So you start with A and you start with B. And, you know, Alice has those. And then we give Bob C, remember B and C are maximally entangled, and Bob goes off somewhere, okay? So then Alice measures her 2 qubits, A and B. She calls up Bob on the phone, says, you know, I got this and this. And then Bob does a little unitary correction operator. And then A, the state that Alice started with, that she wanted to teleport, then swaps places with with C. So this effectively reduces down to the yanking equation. All right, so let's see how this works. So we begin with an unknown qubit that we're gonna call A. And it's, you know, some superposition of being up and down. And overall, we're gonna start off in the state, oh wait, I'm getting the, start off in the state A tensor the cup, all right? Now the question is, what's the measurement that we're gonna make? We're gonna make a measurement in the so-called Bell basis, all right? So for 2 qubits, there are 4 maximally entangled states. One of them we're familiar with. It's just the cup state. Spin up, plus spin down, spin down. And the other ones you can see are just pretty similar. I mean, they're all like maximally entangled, but you know they're a little different in how it works. So for example, you know, in this psi plus state, you know, if you measure one up, the other one's always going to be down. They're always going to be like, you know, anti-correlated and so forth. Okay, so you have these 4 Bell states. And we're gonna make a measurement of our 2 qubits, A and B, in that basis. In other words, we're gonna make a measurement, we're gonna get one of these 4 possibilities with a certain probability, and then after the measurement, those 2 qubits are gonna be in one of those 4 states. Because that's what a measurement is. So, cool, so let's see it work, all right? Here's it sort of written it out here. We start off with A tensor the maximally entangled state. Well, I could have written it as a cup, but whatever. So that's just, let's call it AB tensor 1001, all right? And what is that? It's this big ol' column vector, A00A, B00A. Cool. So now we're gonna form the projector onto the first Bell state. So we're just gonna follow out the possibility. Suppose we made our measurement and we got, you know, answer 1. We can get answer 1, 2, 3, or 4. We got answer 1, and we're gonna consider that case here. So we form a projector. I don't know why I put the little tensor sign there. You didn't need to do that, but you get that, okay? So here it is. Projector on the left times identity. So this projects A and B into the state that we measured. And it acts on a tensor, the cup state. And we see that the overall effect is to get AB 0, 0, 0, 0, AB, all right? And we observe that that is just the cup state tensored AB. In other words, after the teleportation, A has swapped places with C. And in fact, we didn't even need to do any correction. In the case that we get the first Bell state, that we get that just, 25% of the time, or well, depends on the probabilities, but basically, you get that, okay. And interestingly, so if you do the same calculation for all 4 Bell states, right? So again, to recapitulate, you have 3 qubits, you have A and B, and you have C. B and C are maximally entangled, and we're measuring A and B. And then we're looking to see, well, what happens to qubit C? How is it steered because of our measurement on A and B? And we can see that if we got the first possibility, then we end up in a state that's just, the first possibility tensored AB, as we just learned. And so we don't have to do any correction. The qubit, which started out, the A and B, which started out at, sorry, that's confusing because the A and B qubits, but also A and B coefficients. The state of A has now swapped places with C. Okay. But if we got the second Bell state, then C would end up in, with coefficients A negative B, third Bell state BA, fourth Bell state negative BA. You're looking at that and you're like, well, that's pretty much just AB, but there's some negative signs, stuff's flipped around. Okay. One way of thinking about sort of at a sort of conceptual level why this works is that there's an idea that entanglement is monogamous, in the sense that if 2 things are maximally entangled, they can't be entangled with anything else. If 2 things are like less than maximally entangled, they might be entangled with other things, okay? So because entanglement's monogamous, if B and C started out maximally entangled, but then we project A and B into a maximally entangled state, then C is forced to be whatever A was. So then we can use, like up to this sort of like sign flippage and swappage. So we can then use our classical communication, because we have knowledge of the outcome of the measurement, we can correct for the swaps and sign flips. And crucially, we can't do that faster than the speed of light. So like, even though, from the person, so from my perspective, I've just measured A and B, from my perspective, this is like instantaneously or like whatever. I just reason, oh, well, C must be the state that A used to be. But, I can't send my correction over to the person faster than the speed of light. So now in the case that we're, as I was saying, where we just get to the first Bell state, then quite literally the teleportation algorithm just reduces down to the Yanking equation. We have our A, and then, the measurement, the first Bell state is just the cap basically. And so in just that case, it's quite obvious that A is just going to slide its way through. But what happens if we get, some of the other Bell states? And the rule for correcting is that, so if we get the first Bell state, we're going to correct our qubit C with the identity operator. We're not going to do anything. It doesn't need correction. If we get 2, then we're going to do multiply it by the Z operator. If we get the third Bell state, X operator, fourth Bell state, multiply by X, multiplied by Z, where X, Y, and Z are the Pauli matrices. And it's not hard to understand like why that's the case, because what the Z operator does is it flips the sign of the second guy. What the X operator does is it flips A and B, and a combination of, Z and X takes this guy. First it swaps the 2, and then it flips the sign. And so literally, you know, the only error that we had was that we had some swaps of the components and some sign flips, and the Pauli matrices allow us precisely to correct for those things, okay? So, you know, two things make this more powerful than classical communication. You know, although we've sent 2 classical bits, like which are known, obviously, we've teleported an unknown quantum state, which is pretty cool. And B, you know, we've just considered the case where it's considering like a qubit in a pure state that we were sending through this teleportation algorithm. If that qubit had been entangled, then, you know, when it emerges on the other side after being teleported, it's still going to be entangled in the same way. And so, you know, because you might wonder, like in a sort of classical way, like how is this different from like, oh, okay, you know, so like I have a description of something and I send it over there, and then now you have the description of the thing and they're the same, so like whatever. Well, no, it's like, here's an unknown quantum state. It could be entangled with like, Lord knows what. You teleport it, and now it's like still entangled with all those things when it comes out the other end. In other words, you might say at a metaphysical level, it's the same object because it has the same relationships as the original object, not just the same like data. It also has the same like relationships, if that makes sense. Okay. Now it's worth noting that, so, you know, one of the things I want to do next meeting, besides talking about the SYK model, is like actually run this stuff on a real life quantum computer. I was going to do it today, but I don't think we're going to have time. Rigetti has a quantum computer with many qubits, as many as 28, I think. And one of the limitations that you'll find when you're dealing with those systems is that they only let you make Z measurements. In other words, you know, your qubits all start out like, you know, in the up state or down state or something. You can do some unitary operators, and then at the end of the day, you're allowed to make a Z measurement on the qubit, or that qubit, and that's it, okay? So can you just formulate, like, so that's kind of annoying from the perspective of like, well, you know, you want to make a Bell measurement on these 2 qubits. Well, there's an easy way to just formulate the same measurement basically as 2 Z measurements. And so the idea is that instead of a Bell measurement, first you take A and B, the ones that you're, you know, that Alice has or whatever. You do a C0 gate, a Hadamard, and then 2 Z measurements. And the C0 gate is given here. The C0 gate is a cool gate. It's a cool operator. It acts on 2 qubits. And if the first qubit is up, then it leaves the second qubit unchanged. But if the first qubit is down, then it flips the second qubit. And so in general, it's going to entangle the qubits. And the Hadamard gate is here, and it's a cool operator, which sends the up state to superposition of up and down, and the down state to a different superposition of up and down. And what's interesting is that, like, whereas, you know, the up and the down states are basically eigenstates of the Z operator, it sends them to eigenstates of the X operator. And this is just a sidebar, but I mean, the X and Z operators are Fourier transforms of each other. And the Hadamard basically switches between those 2 bases. And you can see that this like has to be true, right? Because the when operators are Fourier transforms of each other, it means they're conjugate. And it means that they generate translations in each other's spaces, which if you have a sphere, and you're thinking about, like, here's the Z up and Z down, an X rotation will swap them. If I just rotate around the sphere, I can take, if I have like an axis that's pointing up, an X rotation will send it down and then back to up. And similarly, if I have, you know, a guy who's pointing in the X direction, a Z rotation will take the X plus guy to the X minus guy and then back. So, you know, often this is framed in terms of position and momentum are Fourier transforms of each other and so forth. But you can see an easy example just because of the non-commutativity of rotations of the sphere. So we love that. Okay, so, and then finally, just a brief word. You might wonder, well, hey, we have this thing, a C0 gate, where we can sort of like control what we do on like one qubit based on another qubit. You might wonder, like, well, what if we just use a quantum operation instead of the classical communication? And so you can actually, so here's a sort of like a somewhat obtuse looking operator. And what it does is it's an operator that acts on all three of our qubits. And if A and B are in the first Bell state, then it leaves C unchanged. If A and B are in the second Bell state, it applies X to C. If A and B are in the third Bell state, it applies Z to C. And if A and B are in the fourth Bell state, it applies, what was it, ZX or whatever. And so, so the point is that, you can formulate that as a quantum operation as well as a classical operation, I guess. All right, we're making good progress. We're getting there. Any questions about teleportation? All right, this is a section that I just thought I would include. It's perhaps not entirely germane, but if you need a little refresher about how time evolution works in quantum mechanics, I'm just going to work through a quick example because some of these facts about time evolution in quantum mechanics are going to become important in the next section. So we have here our very best friend, the Schrödinger equation, which says that the time derivative of psi, which is our state vector, equals -I times E, which is the energy operator acting on psi, the state vector, where I've denoted the time derivative by putting a dot above psi. Okay, so the energy operator, it's a linear operator. It's Hermitian. I mean, that's one of the rules of quantum mechanics. And we can, if we calculate its expectation value, that's the expected value of the energy. One of the most important equations in linear algebra is the one relating eigenvalues and eigenvectors. Okay, so just to review that, if you have the operator E acting on an eigenvector V, it reduces down to just the action of a scalar, lambda, on V. So, oh wait, someone's knocking at the door. Oh, Marty. Okay. So the word eigen, for those who know, means the same in German. So eigenvectors of an operator, vectors which are left unchanged, or better say, unrotated by the operator. Instead, the eigenvectors are merely scaled by some eigenvalue. It can be a little confusing that in quantum mechanics, we're often working with complex vector spaces, and so the eigenvalues can be complex, leading to like a little phase rotation, a complex rotation, but the vector itself doesn't rotate. And furthermore, if the eigenvalue is 0, then we can see that the eigenvector remains completely unchanged entirely because, well, whatever. So, right, as I already said that, operators corresponding to observables in quantum mechanics are Hermitian, which means they're equal to their own conjugate trans. So these have important properties, which have physical meaning. In other words, a Hermitian operator is equal to its own conjugate transpose. So if I take its rows and I switch them with its columns and I complex conjugate it, it is just itself. And this implies that its eigenvalues are real numbers. And so therefore, when we calculate our averages or expectation values, we're going to get real numbers, which is important because these represent things that we can measure. Another great fact about Hermitian matrices is that their eigenvectors are all orthogonal. And so they form a complete basis for the spaces on which they operate. Okay, so what's the Schrödinger equation really saying? It's saying that according to quantum mechanics, time derivative of an energy eigenstate is just given by the state itself times basically -1j lambda. And if lambda equals 0, the state doesn't change at all. So the idea is we describe change in quantum mechanics in terms of those states which don't change in time. If you're in an energy, so the basic rule is like if you're in an energy eigenstate, you stay in an energy eigenstate. You just phase around, unless the eigenvalue is 0, in which case you don't even do that because e to the 0 is just 1. superpositions of energy eigenstates, in other words, states with an uncertainty about their energy, correspond to states that change in time. So this is like pretty deep. Like, I don't think anyone expected this, right? So if you have certain knowledge of the energy of a system, then like that system doesn't change in time. You've like forced its hand. Like you measure the energy, you know it exactly. Well, now it can't change in time. It's in an energy eigenstate. If there's an uncertainty about the energy, then you're going to perceive that thing to be changing in time. So there's many ways to approach solving the Schrodinger equation, you know, depending on circumstance, depending on the kind of problem. Let's just work through a really simple example, just like one qubit. So just brief review of qubit. A qubit is a little spinning object. It can be described in terms of its axis of rotation, which is given by a point on a sphere, along with a phase, which describes how it's turned around that axis. We can easily obtain the axis of rotation by looking at the expectation values of the qubit on the XYZ Pauli operators. So in other words, classically, an object which is spinning is just spinning around some axis, and you can describe that as like, okay, XYZ. In quantum mechanics, that axis is actually an average, all right? So like we can sort of assign this axis to the spin, and it's gonna allow us to calculate the probabilities, but it's really like an average over like many runs of the same identical experiment. In other words, we can't observe this axis of rotation directly, because if we actually measure, we go to measure it, X, Y, or Z, what happens? We project into an eigenstate of that operator. So if you measure the X operator, afterwards, the axis of rotation is either going to be pointing in the X direction or the negative X direction. If you measure Y, it's going to be pointing in the Y direction or the negative Y direction. And so you ruin the thing that you were trying to measure. In other words, if you actually want to reconstruct what is the axis of rotation, you have to do the same experiment, you know, measure X, measure Y, measure Z on identically, 10,000 identically prepared qubits, look at the averages, and then you can reconstruct what that state was. So like, that's the point, right? So like, unlike in quantum mechanics, unlike in classical mechanics, quantum mechanics doesn't sort of present itself to you. There's like a kind of 19th century vision of the light of God being able to like illuminate all things. Well, in this case, there's these, you can't just read out the state of a quantum system by just looking at it. You have to interact with it. Interacting with it changes the thing. And so in order to reconstruct what the state was, you have to do many, many experiments. Repetition is important. Okay. Minor point is that if you have an XYZ, think about the rotation axis, for a pure state, it lies on the surface of the sphere. For a mixed state, it lies in the interior of the sphere. And so if you have a completely mixed state, it's a point in the center of the sphere. In other words, its axis of rotation is like completely unknown. There's complete uncertainty about it. Okay. And then finally, something that's interesting is that if you look at the points, say like Z plus and Z minus, X plus, X minus, Y plus, Y minus, and typical points on the sphere actually correspond to orthogonal vectors, vectors at right angles in terms of the complex vectors, like the qubit vectors, A and B. So this, for those who, attended the original Brooklyn Quantum Meetup, this is some classic shit right here. I was very into this. So, you might wonder, like, is there like a more geometric way of interpreting where those XYZ, where the axis of rotation is coming from? And if you recognize that a qubit is actually, and again, this is really more for, just to introduce this idea, you can look up more about it. And in fact, in another lecture, I'll talk more about this. You can think about a qubit as a complex projective space. In other words, I take some qubit AB here, and then I do A over B. But what if B is 0? Oh shit, we're gonna divide by infinity. A over 0 doesn't make sense. Well, then we're gonna say that's infinity. So now we have a mapping from a qubit to the complex numbers plus infinity. We can go in reverse. Given a complex number, we can form a qubit C1 unless C is infinity, in which case 1, 0. And where we've like ignored the normalization of the qubit. Okay, and it's clear that the qubit therefore encodes, well, it's not clear yet, but what that implies is that the qubit encodes its axis of rotation up to multiplication by a scalar. Then, and this is the fun part, so suppose you have the qubit, you then find this complex number infinity. That complex number lies on the complex plane. Suppose it's this little guy z. In order to find that XYZ point, you just imagine you're up there at the North Pole with a laser pointer, and you point the laser pointer at that point on the complex plane, and it intersects the sphere at a certain point, big Z, all right? And that's called the stereographic projection. And that's the XYZ point. So you can check. You can either calculate the XYZ point, in other words, the axis of rotation of the qubit, by taking expectation values with the Pauli XYZ operators. Alternatively, you can, if you're in the Z basis, you take the qubit state vector, you get a complex number or infinity, you do a stereographic projection from the complex plane to the sphere, and then you get the same XYZ point. And there's there's volumes that could be written about how cool that is, but we will move on. So let's just do like a quick little problem. We're gonna start at the North Pole and we wanna rotate around the X axis. How do we do that? So we're gonna solve the Schrodinger equation in a very classic way, okay? Very, like I'm taking a linear algebra class kind of way. So we're gonna set up our differential equation. I mean, that's what it is. We've chosen X to be our energy operator. So we have the change in time of psi equals negative I X psi. And so we know that our state vector is two-dimensional. And so we're gonna expand it out like that. And confusingly, I'm calling the two components of this qubit X and Y. I know there's a lot of X, Y's, and C's. I hope that makes sense. So what this equation is really saying, like if we, sort of multiply all the stuff out, you could see it in kind of, undergraduate calculus form is saying that the derivative of X in time equals negative IY, and the derivative of Y in time equals negative YX. So there's a standard way of solving such equations. We consider this matrix, which is just negative IX here. O, negative I, 0. We have our famous equation governing the relationship between eigenvalues and eigenvectors that says that the action of a matrix A on an eigenvector is just that eigenvector multiplied by a scalar. Well, if we rearrange that equation, do a little algebraic manipulations, we can see that this implies that A minus lambda I, where I is the identity matrix, on an eigenvector is just 0. And if that's true, it means that that matrix, A minus lambda times the identity, is not invertible because it's sending something to the 0 vector. And if you send something to the 0 vector, you're fucked. You can't come back. No coming back from that. So it's a linear algebraic fact that this implies that the determinant of that matrix is 0. We won't talk about how you know that, but we'll just introduce it. We'll say that we can take the determinant of the 2x2 matrix by we can write it with these, bars, and we can be like AD minus BC, and that's the determinant. So we have our matrix, we set it up, determinant is 0, blip, 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 up. We solve for lambda. Those are the eigenvalues, they're I and negative I. And we could have guessed that. The X operator has eigenvalues plus and minus 1, and we multiplied it by I, so not that surprising. So then, we had this equation before. We said that, A minus lambda I on V equals 0. Well, now we know what lambda is supposed to be. So we try the first case. We plug in I for lambda, solve it out. We get this relationship that the components have to be the negative of each other. And so we're free to choose 1, negative 1 as an eigenvector of the matrix corresponding to eigenvalue I. Although any scalar multiple would do. We could just multiply by any number, it would still work. We do the same for lambda equals negative 1, plug lambda in there, and we get an eigenvalue, an eigenvector 1, 1, okay? And now it turns out, this is not obvious at all, but that is enough information to solve the problem, okay? So we can write down our general solution as, okay, on the left we have X and Y changing in time, equals a linear combination where C0 and C1 are coefficients that we don't know yet, times e to the it and e to the negative it, where we've stuck in the lambdas, the eigenvalues, in that exponent. So e to the I, that's the first eigenvalue, e to the negative I, that's the second eigenvalue, and each one of those terms is multiplied by the corresponding eigenvector. So how do we determine the coefficients, C0 and C1? Well, we have to choose a boundary condition. And as I've said, what we want is at time 0, we want to start at the North Pole, the 1, 0 state. So in order to do that, we just, well, it's pretty easy. You just say, well, at 1, 0, at time 0, we want it to be 1, 0. Da, 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 da. Do a little arithmetic, as they call it. And then you find out that C0 and C1 have to be a half. And so then we can write our solution. Aha, there it is. That gives you the time evolution. 1/2 times this vector, e to the it plus e to the negative it, e to the negative it minus e to the it. Wow. Well, let's watch it happen. So here's some Python code that visualizes it. So we have, this is a little function that just takes the expectation value of a qubit with x, y, and z, so we can get our axis of rotation. Here is a little function which is just this, translated into code. So it's a function which takes a value t, plugs t into that equation, and it gives you a little 2 vector, it comes out of it. We draw a sphere on the screen, we draw a star on the sphere, and we evolve it in time. And if all goes well, which it may not, because Jupyter Notebook is probably, oh, look at that. Oh, it's so cool. Cool, so we did it, look at that. It started out at the North Pole, now it's rotating around the x-axis. Incidentally, yeah, so left and right are the x-axis, up and down are the y-axis, and the z-axis is like into the screen. But there's another way we can calculate time evolution. We can use the so-called matrix exponential. So, you know, we can write our sort of time evolving state as something e to the negative et, where e is the energy, in this case it was x, times psi at 0. This is important to understand. You know, we're not going to dwell too much on it, but I mean, you're familiar with Euler's famous equation, you know, e to the I pi equals -1. It's like interpretation of, you know, complex numbers as like rotations in a plane. And so like in a big way, like we can generalize this. And so like if we have some like Hermitian matrix, then we can, which like represents like a pole, like in the case of these qubits, we've been thinking about these Hermitian matrices X, Y, Z, they represent different axes around which you can rotate. And so it turns out that the exponential, if you do e to the I Hermitian matrix, that's going to be a unitary matrix. And those unitary matrices preserve probabilities and therefore represent, you know, good candidates for time evolution in quantum mechanics, because probability must be conserved. So we can think of e to the negative I x theta over 2 as a rotation by theta degrees around the x-axis. There's a factor of 1 over 2 there, and we won't explain why. Another way of defining, so one way of defining matrix exponential is in terms of this infinite series here, which is most useful when your matrix will zero out if you take enough powers of it. Another way of calculating it is, it can be defined, the matrix exponential can be defined as a matrix that at t equals 0 is the identity, and whose columns represent solutions to the differential equation that we solved before, which sounds kind of complicated, but here I've just worked it out. You know, you can like try to grok this, you know, a little bit. So, we're gonna solve for the first column at time equals 0. So we, you know, look over here, we plug in 0, we get this relationship between the coefficients, we solve for the coefficients, we get a half. And so our first column is going to be that. At t equals 0, there's the coefficients, they have to be in that relationship, we get -1/2 and 1/2. So our second column is that. Putting it all together, we have an expression for the matrix exponential. It's kind of cool, it looks kind of symmetric, right? So this should give us exactly the same as before. Like we start out in the up state, and we multiply it by this matrix, and it should rotate our guy in a circle in exactly the same way. And so here again is the Python code, and it's just a direct translation of the math. And there it is. Okay, great. And then finally, and this way of calculating the matrix exponential will be an excellent segue into what we're about to talk about. Yet a third way of calculating the matrix exponential is to diagonalize our matrix. We can form a change of basis matrix. So this is a matrix that's going to switch from one basis to another. And it's going to be a matrix whose columns are the eigenvectors of negative IE. So we write in there, P, there it is. And actually, you know, if you look at it, it looks quite like that Hadamard matrix from before. So the idea is that we can, you know, act on a vector by this change of basis matrix. It takes the inner product of the vector with each of the eigenvectors, and that's just really expressing the vector in the basis represented by that matrix. But here's the thing. You can transform operators into a different basis, but they require action on the left and the right. So how does that work? So first, we're going to define, so in the 2x2 case, I mean, taking the matrix inverse is really easy. It's just 1 over the determinant of A, and then you sort of swap the guys on the diagonal, and you negate the guys on the opposite diagonal. So then we can pretty much just write down the inverse of P, the change of basis matrix. Then we can consider, well, we have A is our matrix. It's got some eigenvalues and eigenvectors. We're now going to express A in its own basis, in the basis of its own eigenvectors. And when we do that, you know, I don't know if this is obvious, if this was what was going to happen, but in this basis, it's a diagonal matrix. So it's a diagonal matrix, all zeros except values along the diagonal, and the values are the eigenvalues, I and negative I. And what's nice is that in the diagonal basis, the matrix exponential reduces down to the naive thing that you might want to do, which is like just exponentiating each of the components in the matrix. Like that's only true in this case, in the diagonal case. So now we can like write down like in the diagonal basis, the matrix exponential is just like e to the it, 0, 0, e to the negative it. Well, we've got that. So now let's go back home. We do the inverse transformation. Whereas before we did P inverse AP, now we do PD, that's the diagonal matrix, P inverse. And lo and behold, boom, there it is. You get exactly the same thing that we got before. And then finally, in practice, like when you do this stuff, like the way I will generally proceed is, is actually, you know, in a way, something completely different. Just to, so what I have here is I'm going to do an X rotation. This little code here takes the matrix exponential, but instead of asking for it at a particular time, I just do it for some little amount dt. And then when I have like a loop that like evolves my system, and then I just evolve the state by multiplying it by the unitary for just a little interval. And so that's like another way of doing it, which is often useful in practice, like if you're sort of doing like live simulations of things. So this leads us to the main point of this section, which is that there's two equivalent ways of formulating time evolution of quantum mechanics. One is called the Schrodinger picture, and the other one's called the Heisenberg picture. In the Schrodinger picture, it's the one that we're familiar with so far. You start off with a state, and the state evolves in time. You know, you define some energy operator, also known as a Hamiltonian, and you evolve the state in time with that Hamiltonian. You look at the expectation values of interesting operators, but the operators themselves are fixed for all time as a reference. Alternatively, in the Heisenberg picture, the idea is that the state, rather than the operators, is fixed once and for all. And it's the operators that evolve in time. And it's completely equivalent. It's the difference between rotating a point on a sphere and rotating the XYZ axis so that the point looks like it's rotating around the sphere. Okay? So we can time evolve a operator, OT, by sticking it in the middle of e to the iet, e to the negative iet. And the convention is that e to the negative it represents forward time evolution, and e to the positive it represents negative or like backwards evolution. Who knows why? But one thing that's nice is that, like, why does that work? You know, because before when we did our change of basis matrix, you know, that we took the inverse, okay? Well, it's a nice fact that for unitary matrices, their inverse is just their conjugate transpose. I'm about to plug my computer in because it's running out of battery, which may cause the fan to go on, and I apologize for that. Okay, any questions about that? What we'll now get into is some actual wormhole stuff. This was like the setup. Is everyone okay? I've talked for quite a long time. I'm perfectly happy to do this whole thing in several parts, several meetings. You know, if there's questions or discussion, or is this, I don't know if this is a review from any of you or hearing this for the first time. So just pause for a second. Take a little breather. And in fact, I'm gonna let you guys stew on that while I go pee. I'll be right back.
Andre, are you still there? Andre?
Yeah, I'm here.
Did Moshe say that we're going to have something next week, or he wasn't sure?
It seemed like my understanding was that Barry's gonna do that, talk about correction.
Error correction.
Error correction.
Yeah. Which might actually tie into what Matthew was doing here.
I know. I didn't get how I'm supposed to get these downloads. Can you either
Which
explain it
download?
to me or send it to me?
Oh, you mean Matthew's?
Yeah.
Yeah, I'll send it right over.
Thanks.
Yeah, and there's a good book which I know, and it's available online. It's probably a bootleg copy. Nielsen and Chuang.
Okay, write it to me in the email when you send me the.
QIT. I don't know. Well, let me send you this first, and then remind me of the other one. I don't have the other one handy. Sorry, Matthew.
No, that's a good book.
Now we were having. Are you You're familiar with the Manhattan quantum meetup? You were there once.
I was there. Yeah, not nearly enough.
So yeah, Andre and I were discussing that. You should come to that. There's a lot of. You could probably understand what was going on today, which none of us understood.
Well, what were you guys talking about?
Conformal field theory.
Yeah, I have to say that, I understand a little bit of it, and the amount that I understand is largely
and then
wormhole stuff, right?
We were all hoping it would lead to ADS-CFT. You know what that is, Maldacena.
Exactly. Yeah. So,
but Barry McFarland. Do you know him?
Yeah.
He's maybe the brightest guy in our group. He's a mathematician, and he's more interested in the math. And most of us are really leaning more towards the quantum physics or the quantum field theory and GR. So there's kind of a little disconnect there, but.
Yeah, Matt.
But you should. We do ours before yours on Sunday. Sunday at 1 p.m. It's
Okay.
the quantum. What's it called, Andre? The Quantum Mechanics, New York Quantum Mechanics meetup. Yours is the Brooklyn.
Maybe it's New York quantum field theory.
No, it's not quite. It's called quantum mechanics. They don't even, but it is quantum field theory. Matthew, are you in Philly now, or are you in?
I am. Well, yes. I live in Philly, although right now I'm in New Jersey.
Oh, but you're not back in Brooklyn, are you?
Home. No, I'm not back in Brooklyn. I may have moved away, but Brooklyn's still in my heart.
Spencer, you know Spencer. Of course, you know Spencer.
Yeah,
your neighbor. He actually gave a presentation at our meetup.
That's awesome.
Then he moved to California.
Oh, okay. Yeah, I haven't talked to him recently. I was wondering.
Yeah, we haven't either. Now, he gave a presentation probably a year ago.
Mm-hmm.
Right after you moved out of Brooklyn. He came to some of our meetups, but then he suddenly moved back home. I guess his home is California, right? Yeah.
Well, his line of work, he and his wife are just flying around like crazy. They're cinematographers and stuff. So
the Manhattan group
he's
is
the cinematographer.
The Manhattan group is called New York Quantum Theory Meetup.
Quantum theory, okay. Covers everything.
Very nice.
Is that young man your brother?
Yeah.
The other guy?
Yes.
Did your father say he was there? Which one's your father?
It sounded like he was with my brother.
Oh, okay. Because he asked me if I was Marty. And I said, "Who are you?" He said, "I'm Matthew's father, but I see your brother. I don't see him. I don't know. Is your brother still here?"
Unclear.
Yeah, there he is. Julian and Insange. What is the origin of the name Insange?
His name's Julian, and he's insane.
Oh, insane, because it says Insange.
I'm pretty sure that from the very beginning, there's been ambiguity about how to pronounce it.
What was that?
It's always been confusing about how to pronounce it, I have to say. He's had it that's like his email or whatever. He's been like that for years.
Oh, okay.
He's an app developer and a computer programmer, and he's right here, and he's quite a talented guy.
This is what I look like. If anybody wants to talk to me, feel free to email me anytime. I'm just insanej@gmail. I'm not sharing video because I'm here eating dinner, so I figured that might be a little disruptive, but we're here.
All good.
But Julian, there's a different picture of you. There was a different picture of you.
Well, this is a video. Come on, I'm alive. This is alive.
Oh, I thought the other one was alive too. I just thought you were still. You look like a little kid in the other one.
Yeah, no, that was like 5 years ago. Yeah, that was many years ago. Yeah. Anyway, just thought I'd show my face so you'd.
Oh, good. What's for dinner? Can you send some over?
I wish. I'll show you. We're having chicken and potatoes. Got a little bit of broccoli.
Oh, nice wine. What kind of wine are you drinking?
That's some nice rosé, upstate New York. We really love it.
Nice.
Oh,
Yeah.
okay.
It's a really good bottle.
Really delicious. Bully Hill Farms. But yeah.
Okay, great. Bon appetit.
Thank you.
So, how you guys feel? Should I continue on a little bit, wormhole style, or are we feeling a little? It's 5:40. We're coming in on that mark. I don't know if anyone has plans later or like what people's.
I'm going over to Julian's to eat.
How much explaining do you have left to do in this, Matt?
Well, if I can get through, the next part, which, I guess what would be nice is to, I have like a little code that runs the wormhole simulation. So it would be cool to get that so you can see it. Like, it has a sort of dramatic feel to it. Go in, get scrambled up, and rear its head on the other side.
Okay, let's do it.
Okay, so we're going to talk about something called the thermofield double state first. We're gonna sneak up on it a little bit. So we have our, what you might call our original discovery. operator on the left acting on the maximally entangled state is the same as transpose the operator acting on the right on the maximally entangled state. So let's consider the case where we choose some energy operator E, and we define E on the left to be just E tensor the identity, and E on the right to be identity tensor E transpose. We can then consider the time evolved versions of those operators. This is sort of why I went into the background about time evolution. So we can write the time evolution of OL as E to the IET O times E to the negative IET tensor the identity. Effectively the same on the other side. And so now we realize that we could actually sort of generalize our equation before in such a way where it refers not just to left and right at one time, but an action on the left in the past corresponding to an action on the right in the future. And if you know this nice fact, which is that E to the negative IET transpose is just E to the negative IE transpose T, then this becomes a simple consequence of the diagram language. You see, we have E to the negative IET, O, E to the IET, and then we just slide these guys around the cup. And then they go to the transposes of themselves. And essentially, by visual inspection, we've proved that this is true. So now we're going to consider a generalization of our setup. And now things are looking like wormholes a little bit, you know, mainly aesthetically. But so what we're going to do is, before we're just considering like, just 2 qubits right here. But now we're going to consider this case where we have a left and a right, but the left and the right are divided up into an A and a B. So we have A and B on the left, A and B on the right. And, when it comes down to like the actual wormhole thing, the idea is that the A's are going to be like our message part. So we're going to like throw our message in there in A left, and it's going to pop out in A right. And the BL and the BR are going to be the quantum states of the 2 black holes. All right, so that's where we're going to go. So the question is, like, we now need the generalization of the cup state to more than one dimension in order to, we still want to be able to slide these operators in the same way through this. So, the generalization of the cup for any dimension is just, given 2 Hilbert spaces, they have like the same size, you just go through iterate through the different basis vectors, and you do them tensor times the delta, Dirac delta, which takes 2, it's just like a function, it takes 2, well, there's all this question about what the Dirac delta is, but it takes 2 arguments, I and j, and it's 1 if they're equal, and it's 0 if they're not. So basically, the only things that contribute to the cup state are when the 2 states on the left and right are in the same state. And so now we sort of reason, well, we're like, well, look, it's kind of interesting. So if like this is true, we can take this crap on the left, slide it around to the right, then, supposing we keep the stuff on the left, we can just assume it's true on the right. And then, like, why don't we, like, if we want to have O, T emerge on the right side, it would suffice to have a little time evolution on the right side. So I'll just show you the picture. So here, this part is the same as before, but we've just added this extra bit of forward time evolution on the right. And because of this, you see, when you drag this guy around, these 2 just cancel out. And so then O swings free, boom, coming out. So now you could wonder, there's like a generalization of this. So far we've been considering operators, but what about states? Can states go through the tube too? So we can think about this like in terms of a setup where we have now, the A's and the B's, lefts and the right, and we have this like message qubit. And the idea is we want to swap it, do the swap operation between M and AL. And, you very quickly notice that this is not going to work anymore because now there's like this obstruction. Like you can't move this O, you can't slide this O around the big cup because of, you can just see visually in terms of the threads, there's this like obstruction here. O tries to go down, it gets like distracted over here, like, oh shit, can't do it. So the question is like, can we, come up with like a generalization of what we've been talking about where like you could? How can we remove that obstruction? Similarly, another generalization we're going to consider, and in fact, it's the same generalization, is what if we don't use the cup state, but instead use what's known as a thermofield double state. And the point of thermofield double state is it's like also like a maximally entangled state or very entangled state. But it's entangled in the energy basis. So here, here's just this sort of operator attempt to, at an operator, is this true? Does this work? It works for the cup state, does it work for the TFT? So what's the TFT? Here's a little definition of it. Okay, it's got a little normalization, little partition function there or whatever. And it's a sum over the energy eigenstates tensored together of some energy operator. The line above the EJ there means conjugate, complex conjugate. And it's defined in terms of this parameter beta, which is the inverse the inverse temperature. So as beta goes to 0, temperature goes to infinity. Wow, is that okay? Yeah, it's fine. The idea, and what's interesting is that in the limit of infinite temperature, the thermofield double state is just the cup. So basically you can treat like all of the previous discussion as like being true about the thermofield double state at infinite temperature. And the question is, if we're at some finite temperature where they cool it down, are many of these statements that we've been making still true? And we bring it up because the thermofield double state is apparently a good model of these, two-sided eternal black holes that are described in these pictures. The idea is that like the two black holes start out in the thermofield double state at some temperature, because black holes have a temperature. That's what, Stephen Hawking tells us. So, here it's like materially, message inserted means like we took our qubit and we like swapped it in for AL, and then some stuff happens, okay? And so far, the message just hits the singularity. Why? Because like there's this like obstruction here. There's no way for it to get through. Okay, so the question is, how can we fix this problem? Okay. So, we already saw that. Okay, so what's the solution? The solution obviously is this diagram or whatever. We're gonna insert our message, then we're gonna like couple the black holes. And like, it's like from the perspective of these black holes, this introduces a negative energy shockwave that's coming in from both sides and then hits the singularity. Well, you see what happens is that as the message is like going through the geometry, when it hits the negative energy shockwave, well, it's negative energy. So it gets translated back in time and it ends up in a place that happens to be outside of the event horizon, and so that can come out. Okay, easy enough to say or like whatever, but what does it mean in terms of, our qubits and stuff, okay? So here's the full picture. All right, and this is just, literally what they have in the paper, the reference paper that I gave you guys. So, this is it. This is like the wormhole, whatever protocol, okay? And there's two cases, state transfer and operator transfer, okay? So the idea of the state transfer is we start off with a qubit and the thermofield double state at some temperature. We have AL and AR on left and right, and those are gonna be our message qubits. BL and BR are gonna be our carrier qubits. You can think about them as just being like, the black hole microstates or whatever. Well, I guess you think of AL and AR as also being part of the black hole too, but whatever. Anyway, so what's the protocol? First thing you do is you evolve the left side into the past. And then you swap in your message. Then you evolve the left side into the future. So you start it at T0, evolve backwards in time, insert your qubit, evolve back to time 0. Then you have this coupling. That's the new part that we've introduced here. E to the I, G, V. I haven't told you what G is, haven't told you what V is. But what you can see is that it only acts on the B's. It's that's the cool part, right? So it's not acting on the message subspaces. It's just acting on the B's. And then we couple the left to right side, and then we evolve the right side forward in time. So again, start time 0, evolve backwards in time, insert the message, evolve forward in time on the left, couple the left and right, and then evolve forward in time on the right. And then the idea is that AR should just be M. It's gone through the wormhole. And similarly, in the case of operator transfer, whatever. So, okay, so we have a lot of questions still to answer. It's does this work for any old energy function? What's the G? What's the V? Okay, so I won't motivate why we're going to choose this V. It'll become clear as we go on. But one operator that does the job that's given in the paper is this one, which is just a ZZ coupling. So it's B is the number of qubits in one of the B systems, like say BL. A is the number of qubits in the A system, in this case just 1. And we sum over the Z operators on either side. So I've drawn it out here, right? So it's you would take just the Z operator acting on this part of the carrier subspace or whatever you want to call it, the B subspace. And you multiply by the Z operator on this guy. And then you take the Z operator on this guy and you multiply it by the Z operator on that guy. Take the Z operator on this guy, multiply by the Z operator on this guy, and you add them all up. And crucially, this coupling is diagonal. It's like a diagonal matrix. And so it's actually classical, non-commutativity. It's completely classical coupling. And in fact, we'll see that you can actually do something completely analogous to quantum teleportation, where you, instead of coupling the black holes with a field or something, you measure the black hole and then do some stuff to the other black hole. Okay. So, all right, so this is a cool part. Okay, now this is a little bit of reasoning right here. Okay, so it's suppose you're in the thermofield double state, okay? And you take the partial trace. You get the partial state of A and B, all right? And then we're gonna write that rho beta. And then we're gonna consider the square root of it, okay? So the square root of rho beta, this is whatever, rho beta square root times itself equals rho beta, okay. Well, we can just write that down directly. We don't have to form the thermofield double state and then take the partial trace. It just turns out it's the same on the left and the right, and it's just e to the negative 1/2 beta e over that little normalization. And so it actually turns out that we can use that to prepare the thermofield double state from the cup, okay? So this is really interesting, right? So so TFD is just the identity tensor, what did I call it? Whatever, the partial state, acting on the cup, It's the same thing as if the partial state was acting on the left, and they both give you the TFD. In other words, what does that imply? Like, what do we know? Like, what do we know? We know that if you take an operator on the left and you multiply it by the maximally entangled state, it just takes that operator, which is like, you know, a square, and it strings it out as a vector. And so what this implies is that the vector of the TFD state, if you take that vector and form it into a matrix, you just get this partial state rho. And if you take the partial state rho and you multiply it on one side of the maximally entangled state, it just strings out that matrix into a vector and it gives you the thermal field double. And this is gonna, so we're gonna use that. We're gonna work that, okay? So before we had, you know, operator acting on the left in the past on the cup state equals transpose the operator on the right equals a cup state. Now we want to use the thermal field double state, okay? But we know what that is, right? We can like expand this out. We know the TFD is just rho half times the cup, okay? Where we've just decided to act with the rho that acts on the right. So you see rho at beta, at inverse temperature beta on the right. And why did I do that? I could have done left or right, but I very specifically chose right because you see this product here is O on the left times rho on the right. One acts on the left, one acts on the right, which means they commute. So I can switch their order. So I'll write it instead as rho on the right times, you know, OL negative T on the cup. But what do we know about, you know, OL negative T times the cup? That's just ORT, right? OL negative T times the cup is just ORT. OL negative T times the cup is just ORT. So now we've been able to write the action of OL in the past on the thermal field double state is just rho right times operator transpose on the right times the cup state. So we've just been able to like formulate the TFD in terms of the cup. Similarly, we can do the same thing for the other operator. You know, we know that the TFD is equal to rho on the right times the cup, and then we have just rho on the right transpose. And so you see that the only difference between these two things is the order of these factors. Whether we take rho beta times ORT or ORT times rho beta. And so those operators must be adjoint to each other. They're just switched around, okay? So without missing too much of a beat, I will now kind of give the punchline of the whole story, and then we'll see the example. If it'll load. Getting there. Talk a little bit about this thing called scrambling. And actually, this is the part that is like perhaps most related to the, if any of these things could be said to be related to the coronavirus, in the sense that spreads, consider them like interacting. There's some like random unitary operator that just like acts on all the qubits. You know, if we wanted to run that unitary on a quantum computer, you know, we'd be interested in cutting unitary down into a sequence of gates that act only on 1 and 2 qubits at a time. And so if you think about 1 qubit is, you know, they all start off separable from each other. And then, you know, at time t, this qubit, you know, interact with that qubit, and then like those two go off and interact with these qubits, and then those go off and interact with these qubits. Entanglement's going to spread among the qubits like an epidemic, like as soon as, you know, one touches it. So there's a nice way of thinking about this, which is what we could do is, okay, we have a bunch of qubits, and we're just going to define some like random energy function that's going to act on them, and they're going to start off in a separable state. Meanwhile, we're going to have a maximally entangled state of 2 qubits, okay? And then we're kind of do what we were doing before. We like take one of those qubits and swap them for one of the guys in the group, okay? And then all those guys are going to get entangled. But that, you know, we started with a pair of qubits. There's one guy that stays outside, okay? So you have like a pair of qubits. One guy stays, they're maximally entangled. One guy stays outside. The other one goes in and gets scrambled with the rest. But because they were entangled, it's kind of like Ariadne's thread. There's a kind of thread connecting these 2 qubits so that you know, you can sort of keep track of them. You kind of follow the thread home. So what we're going to do is we're going to look at how, over time, the entanglement between all the qubits in a group with the one who stays outside changes in time. All right, sorry, that was like a little torture way of saying it. It's
Right,
worth
just to
noting
let
that,
you
you know,
know-
if you want to.
Hey, Matt.
Yeah.
I don't know if everyone else is getting this, but you're sounding a little Mr. Roboto for the past like couple
Oh,
minutes.
really?
Yeah.
Yeah, I saw my image was getting a little choppy.
Yeah.
Is it okay?
We can still understand you, I think, to a certain degree. You just, I think, I don't know if it's internet slowing down or what's going on.
Yeah, there's like some weird. All right, let me unplug my computer. Yeah, yeah. Let me know if that. Here, I'll close some windows. And, you know.
Yeah, maybe that would help. I'm not sure.
All right. So, classic
Much better
thing.
now.
Oh, great. That's funny. How's it?
Yeah.
A classic measure of entanglement is the entanglement entropy, also known as the von Neumann entropy, which I just give a little formula here. You can calculate what's known as the quantum mutual information between 2 subsystems using this equation. Let's not dwell on it too much. Because we got some cool graphics. Let's get on to that. Look at that. Oh, wow, weird. Wow. I don't know why it's not supposed to be.
Yeah. So it's supposed to be solid bars.
Yeah, they're supposed to be solid bars. Oh God. You know, I tell you, these notebooks, it's like in theory, it all works, but well, all right, guys, chill for 1 second. I'm just gonna open this up on the outside, you know. Quick. Test. Oh yeah, there it is. Okay, look, so it was like most entangled with the first qubit because we just like swapped it in. And now you can see over time, the entanglement with each of the qubits in the group is like varying, and like very quickly, you saw that the entanglement spread throughout the whole system, and now it's just kind of like waving around. So again, it's like we had 5 qubits in a row, and then we had like, you know, 2 qubits that stayed outside. We swapped one of those qubits with qubit 1, so that at the beginning, the one that remained outside was maximally entangled with qubit 1. Then we evolved that whole group, and we saw that like entanglement got very quickly spread out over the whole system. I'll run it again. So we start off, it's like mainly maximally entangled with 1, that goes down, the other ones go up. So, okay, there you go. There you have that. All right. So just as like we can keep track of the qubit as it gets scrambled, you know, among a bunch of other qubits, we can also keep track of an operator. So like an operator, like, you know, might start off like it only acts on like one qubit or something, like one little tensor piece. But if we evolve the operator in time, generically it's gonna become supported over, you know, like the whole Hilbert space, okay? So like, it's worth mentioning, you know, that, you know, just as quantum states form a vector space, operators form a vector space too. And in terms of how this works, you know, the classic example is that like any Hermitian matrix can be written as like a 4-vector, like a linear combination of Pauli operators. So if I have some t, like 4-vector t, x, y, z, I multiply t times identity plus x times Pauli x plus y times Pauli y plus z times Pauli z, and I can express any, you know, 2x2 Hermitian matrix that way. The fact that it's like a 4-vector is like really important, like not for us, like right now, but like, yeah, like it's very, very cool thing. Now, you can, you know, go in reverse. Suppose we have some matrix H. We could take these traces with the Paulis and recover the 4-vector. And I think there's a factor of 2 in there as well. Alternatively, we also know something else, which is that, you know, we can take these traces between matrices to get like their inner product, but we know we can also turn operators or matrices into vectors using the cup state, right? So we can also write that same thing as like, you know, these expectation values where it's like X on the cup against H on the cup, Y on the cup. So we've just basically, you know, it's kind of trivial in a way. We've just taken all the operators and turned them into vectors, and then it's just the standard inner product there. Now the question is though, that like works for like 1 qubit, but like what about, you know, any dimensionality? And yes, there's like a basis for Hermitian matrix for any dimension, but we're specifically interested in like powers of 2 dimensions. Like in other words, like systems of qubits. And it turns out that like all the combinations or the product of all the Pauli operators gives you a basis for matrices. In other words, I can write a, if I have a 2x2, you know, matrix, sorry, a 2-qubit operator, so a 4x4 matrix, I can express it in a basis formed by these 16 operators. And, you know, what's cool about that is in terms of these operators, we can define a notion of size in the sense that we can say that, like in this case, the identity times the identity is size 0, all right? These guys, xi, yi, zi, and ix, iy, iz, they're of size 1. And the other 9 operators here are of size 2. So the idea is that the size is the number of non-identity operators. And that's kind of cool, right? Because like what we're interested in is like how operators get like scrambled out. So like what we should expect is like generically, you know, the size of operators grows. And we can see it happen in real life using computers. Where I avoid the notebook yet again. Bum, 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 bum. See, that's, you gotta take this out. Sorry. So, so what you're gonna see is we're gonna take a random operator. Actually, we're gonna start with the Pauli X operator acting on like 1 qubit. And then we're gonna evolve it in time. And we're gonna see the probability that it's one of the operators in the Pauli basis. Okay, so here we are. We start off, and it's entirely xi. We start off with x, it's just, you know, x on the first qubit. And it's evolving, but it's happening painfully slowly. I apologize for that. Let me increase the speed. Am I coming in okay?
Yeah.
Like, all right, good. Computer's getting a little I'm crazy. Try that again. I adjusted the speed. It'll go faster. All right, there we go. Look at that. Look at that. Oh, almost immediately, scrambling. We're scrambling around town. Now, of course, like this is not like, you know, I've arranged these like linearly, like I, Ix, Iy, Iz, Xi, Xx. So like this is not like literally organized by size, obviously. But yeah, you can see. So like as you're interested, you know, it's like what happens to operators, you know, in the Heisenberg picture, they just become supported across, you know, generically like the whole Hilbert space, you know, after like a very short amount of time, like for randomly chosen operator. Yeah, it's kind of cool. Look at that. Sometimes it'll spike. Anyway, so there's that. Great. So now, all right, we got our setup. Okay, so here's the punchline of the whole thing. And it's the thing that is like, as far as I can tell, the, you know, one of the innovations of this paper that I've directed you guys to. And for some reason, it's just like very, okay. So the question is, you know, this is all well and good, but for our wormhole to work, like what requirements are there on its energy function? It's like, will any one work? Do they have to have some special structure? You know, the idea of throw a qubit on the left in the past, it gets scrambled over the whole left side. And, you know, the idea is that we're sort of treating like the qubit getting scrambled over the black hole as the qubit going deeper into the geometry. And this is the connection to the ADS CFT. Like here it is, okay? Like the idea that like the quantum state is like the CFT, right? It's this qubit's getting scrambled over the whole CFT. These qubits are a stand-in for the CFT part of the correspondence. And then the idea is that there's like an emergent geometry, that's the ADS part. And the idea is that like the more the qubit gets scrambled over this quantum state, we regard it as being more deeply inside the emergent geometry defined by that quantum state, okay? So you have a qubit, throw it in, gets scrambled, and then we have some of this coupling, and then it gets unscrambled. So it turns out that, you know, operators, like energy operators that have like the right scrambling properties, basically can be described as having so-called perfect size winding. And even if it's not perfect, like it could still kind of work. The SYK model, which we'll talk about like next time or whatever, in a limit has perfect size winding, for example. And so it can be interpreted as like a semi-classical wormhole. Not all the examples can be interpreted as like semi-classical wormholes, even if information can be transmitted. Okay, so here's an ansatz. So like this is, you know, this is like not like a proof. It's saying like, supposing that like our thing has this form, then it'll be true, all right? So we had this state here, you know, OL negative T on the TFD equals our little rho guy, ORT on the cup or whatever. So we just look at that and we ask, you know, what is it like when we evolve, like time evolve that thing? And if the Hamiltonian has perfect size winding, what you find is this, that you can describe it with this ansatz, which is a sum over Pauli's, where Pauli's are P, where RP is just, you know, some real number, it's a coefficient, who knows? But the crucial fact is that each Pauli operator has a phase, e to the alpha P over n. where that P there is the size of the Pauli basis vector. In other words, so the sum is over all the, n qubit Paulis, where n is the number of qubits on one side, because you see here that both the rho and the O act on R. So in the Pauli basis, the size winding Hamiltonian basically gives each Pauli basis vector a phase proportional to its size. In other words, the phases, like in the Pauli basis for each basis vector, wind around at like a speed proportional to the size of that operator, okay? And then considering that rho ORT and ORT rho are just conjugate to each other, we can write it out like this, that O acting on the left in the past on the thermal field double state is equal to this, where, what have we done? Like when I've written it up here, P is an operator. We have an operator evolving in time, and the Paulis are operators. But of course, this could be equally described as like, we could take the operator act on the cup state and get a vector representation of the operator. You see all these things kind of like occurring. So, we can write this as just this. We could write it as, sum over Pauli's e to the I alpha size over n times some random coefficient times the Pauli operator acting on the cup, or we could just regard that as just a state itself. There's two different ways of writing it. And crucially, because these guys are, the dagger of each other, because they're just swapped, these are going to be conjugate to each other too. In other words, the only difference when we're dealing with this TFT stuff, the only difference between acting on the left in the past and acting on the right with the transpose in the future is the direction of in the Pauli basis, whether it's clockwise or counterclockwise. And this is the central insight. Because what it means is that in order to complete our transfer and make the wormhole traversable, it suffices to do something very simple, which is just unwind the phases. And it turns out that our V operator that we chose before is enough to do the job. And finally, I will say that when beta is 0 and we're at infinite temperature, when the thermofield double state just reduces down to the cup state, then if you look at rho times ORT in the Pauli basis, because that operator is Hermitian in that particular case, its components are real. And therefore, there's no question of a phase. And so as we know, like for operator transfer, like with the cup state, it just worked. Like we didn't have to even do the coupling. But not that, so that's true for operator transfer, not for state transfer. So, okay, so ta-da. So like now let's just like look at it. So I have some examples of the code that just, basically just does what I just said. And we can look at it in a couple different ways. And that'll be it. Thank you guys so much for listening. I know I've talked for a long time. I really appreciate it. Means a lot.
Yeah, thanks for doing it.
Yeah.
So it's so slow, baby. It's so slow. Do do do. This. Okay, so the first thing to say is like, let's just, choose a random energy operator. It's not necessarily going to be perfectly size winding, but like actually randomly chosen operators are pretty often scrambling, you know? So it might not be totally crazy to do that. So what does this code do? So the final thing that like I haven't given you is, you know, we have the qubits and the whatever and this and that and the V and the E and the whatever. The one thing we didn't say was what's G? The coupling was E to the I G V. What's that coupling strength, G? And the idea is you just got to figure it out. In other words, what I do here, we now have this plot, which is unlabeled, I apologize. And the idea is we do the teleportation as the wormhole protocol. Like here it is in this one function. So here's E, this constructs the thermofield double state. Here's our message. We tensor the message with the thermofield double. We construct the coupling. Here's the wormhole, right? So here it is. We act on the state, evolve the left part, back in time, swap in the qubit, evolve the right, forward in time, do the coupling, evolve the right, forward in time. And then what we do is we look at the, you know, qubit on the right where, you know, our thing is supposed to emerge, and we look at its Z expectation value. And the idea is we're going to throw in a qubit in the up state. And the question is, so, you know, it starts off the state where the expectation value of Z is 1. And so what's the expectation value, you know, when it comes out? Like, so if it's like really, so the thing is though, when we go from one side to the other side, everything's transposed, okay? So actually, we're gonna get the opposite. In other words, because we threw in a guy that was up, we're gonna get a guy coming out that's down. And what we're gonna do is we're gonna iterate over different possible values of the coupling G and see what the expectation value of Z is on the qubit that comes out of the wormhole. And here you have it. And they always have this structure. So, you know, we can see that, say, like for this, where G is about 2.3, that's pretty good. We have, you know, it goes down, and it's not perfect. I mean, it's supposed to be -1. It's only -0.4. But, like, that's fine, you know. After all, how many qubits? So this is for 7 qubits, by the way. So I have 7 qubits on the left, 7 qubits on the right, and you know, and this is also an infinite temperature. So like beta equals 0. So, you know, if you play around with this code, you know, you can change the number of qubits, you can change the temperature, change the starting state, whatever you want. This I will now show. In the paper, they give a example of a system that they like that in some sense is maximally scrambling, in the sense that if you look at the entanglement entropy of subsystems that begin in separable states, they grow like as quickly as possible, evidently. And it's called the kicked icing model. And it has a kind of an interesting time evolution because it actually is evolved in like 2 pieces. So one piece, here, quite small, right? So one piece is the icing model, UI. So this is just a classic icing model. You see it's a sum over couplings, Z couplings for adjacent qubits, and then like an overall Z guy here. So this is just like an icing model. And then the kick is this part, which goes in the X direction. And the idea is, for the kicked icing model, it's like you evolve the icing part and then give it a kick. Icing, kick, icing, kick, icing, kick, okay? And there's some parameters, which are J and B here, and these HIs. And it turns out that if J and B are pi over 4, and the HI are, you know, Gaussian, then things are cool. So, you know, let's look at it. Ah, crap. Wrong one. Oh, gotta change that too. So I bring this up because the plot that I'm about to show you reproduces like precisely one of the graphs in the paper. So they're like, we use the kicked icing model, 7 qubits, infinite temperature, et cetera, et cetera, et cetera. And then you see this like particular graph. And this, what you're about to see is just basically very similar to it. And so I just bring it up to, you know, so slow. Well, while that's chugging away, oh, whatever. I generated it before. Who cares? We won't do it live. It just looks like that. And so this is a classic thing with the G coupling. It's, you know, it's gonna be periodic, and, you know, it basically goes down to about zero, negative 0.4. So here's a nice point, which is that I mentioned before that, you know, this whole wormhole thing is a generalization of quantum teleportation. So you might wonder, I've like said that the coupling is actually a classical coupling, it's diagonal. So could we, you know, instead of coupling the left and right, could we do a measurement on we take all the qubits of the black hole on the left,
We didn't hear what you said.
make
Could
a
you
Z
repeat
measurement.
it?
Oh yes. So we go over all of the qubits on the left, not the message qubit, and then we measure in the Z axis, okay? And we get plus or minus 1, and the states are projected, okay? So then we act on the carrier qubits on the right, and we act with this operator, e to the IG, sum over, you know, all the qubits we're gonna act on, of the Z operator on that qubit times the eigenvalue that we got before. So in other words, if I had 3 qubits over here, you know, I'd measure Z, 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 and I get like, say, +1, -1, +1. And then I'd have my 3 Z operators on the right. And, you know, I would do like, whatever, what did I say? 1 times Z on this guy, -1 times Z on this guy, 1 times Z on the other guy. And if you do this, then it works. It works as before. So what we have here is, you know, some code, you know, basically similar to before. You know, we construct our thermal field double, construct our coupling. This will optimize our G value. It'll just like sort of run through the, you know, the wormhole protocol, you know, trying different G's out. And, you know, then we go, once we've figured out what a good G value is, we go through and we're like, all right, so do the protocols before, and then do these measurements. So we do measurement on the guys on the left in the Z basis, and then apply the unitary correction. And I will just leave it at that. That's what we got before. I won't try to run it. I apologize. Because, you know, this last one is actually the really cool one to see kind of like visually, I suppose. So this one is like, we're actually gonna see it animated. We're gonna do the same thing as before. We're gonna take 2 entangled qubits. One's gonna stay outside, the other one's gonna jump into the wormhole. And we're gonna look at the entanglement entropy between the one that stays outside and all the guys on either side of the black hole. And we'll watch it evolve over time. I apologize for how slow this is. I have to say, my computer has been acting up recently. All right, let me just terminate that real quick. You can see it's like a little, it's just so slow. Good God. Go, 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 go. Do it. Oh, there it is. Okay, look, boom. Okay, there we're evolving. So it's mainly entangled with the guy who's like right outside the horizon, and we're evolving the left black hole in time, and you don't see it change because it hasn't fallen into the wormhole yet. Remember, like the first step is to evolve it back in time, and unfortunately, this might take a long time. Oh, there it is. Okay, now we've swapped the qubit in. Now we're time evolving forward on the left side, and we see that the qubit has gotten scrambled. It's all scrambled up on the left, and that goes on for a while. Kind of entertaining, I guess.
Mm-hmm.
Uh,
Another question.
Yeah.
Not on topic, actually. Have you ever tried importing a JavaScript library into a notebook?
So, it's a good question. Oh, by the way, look, the coupling has initiated. I just want to mention that. And you'll, in a tiny way, be able to see stuff start to appear on the right. Anyway, yeah, so like VPython, which I was using for the 3D graphics, like technically it's like written in JavaScript or like whatever, and it can run as a standalone thing or as a like in a Jupyter notebook. As far as like running JavaScript code directly in the normal Jupyter notebook, I don't know if there's a way to do it, but there's like a couple different companies or like services that like allow you. I can't remember the name of this one. I'm thinking of it, but it's like it lets you kind of have like blocks, one block's like Python, another block's like JavaScript.
Yeah. Oh, yeah. No, I've been doing that. But my problem is that because of limitations on JavaScript, that globals and locals are treated differently. And you have to have them, if you import a library, you have to have it in the same block in the notebook, which is a pain in the neck.
Yeah, that is really annoying.
Yeah. So I was wondering if you had done it some way, maybe.
Yeah, well, actually, a couple of months ago, I was like working on a thing, like a kind of JavaScript Python bridge. So you'd like have you'd like define like a Python object and, it'd be running on some server and there'd be like a client and it would have like an equivalent JavaScript object and then they'd like synchronize. That was something I was working on.
Okay.
Yeah, I can talk a little bit more about that.
Yeah, if you find something, I'd like to be able to do that, just define my
mess. It's like Python's so good for all the scientific stuff. I just find that, yeah, like all these there's so many different kinds of like notebook type things and whatever, and like each of them has like a certain kind of flaw, like, So I'm sorry, I must have put the DT on this guy to be very slow. Oh wait, it's coming in! We got a guy coming in! Oh, it's coming out of the wormhole, there it is! There it is! Nothing else, you've seen it here. Thing went in the wormhole, came out of the wormhole. That was it. That's what we were fighting for right there. Okay. Yes. Wait, let's just do it again, but like maybe like a little faster. It was kind of like a little lame,
Matthew, did you record this whole thing?
Yeah. It's probably the reason it's a little slow. Yeah, I'll put it up on YouTube, like with your guys's.
Yeah, that would be great.
Yeah, totally. Bum, 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 ba, ba. So, all right, well, we'll let that fizzle over there. So, okay, like the final one, I won't like dwell on this, maybe. It's just, instead of like time evolving it, the protocol like step by step, like what we've been doing, kind of like, instead you could just do it like kind of continuously in time. So we just sort of define the energy operator to be like, energy on the left, energy transpose on the right, plus the coupling. And we can just, see as we just like continuously evolve in time how the thing how the thing goes. This is the same one as before. I just yanked up the speed, and you see that it's very choppy now, but I mean, whatever. It lets you see, yeah. So it's like, you notice the coupling kind of has a different feel than the scrambling, and really should zoom in more so you can, oh, there it is. Look at that. Look at that wormhole right there. That's a great worm. All right, let's just do the continuous time one really quickly, and then we'll conclude, I guess. So, I mean, like, one message to take away from a lot of this stuff is that, like, you know, there's an extent to which these ideas like ADF, CFT, and the holographic correspondence and stuff like that are like wrapped up in like really fancy stuff. Like, you got to understand, I'll take these crazy integrals and your conformal field theory and your strings and your this and your that. But, you know, these days, you know, people have come with like really clever ways of just using like really simple models, qubits, to implement the same principles. Hey, because, you know, we have them in the lab now, we have quantum computers. And so, you know, you can just think to yourself, like, what would be a cool Hamiltonian? Is it going to be scrambling? Might it have perfect size winding? Come up with it with your brain, and then check. Is it size winding? How many qubits can I send through it? You know, how can I think about, you know, whether it does in fact have a geometric dual? You know, these things are actually within reach of like, you know, ordinary mortals, as they say. So this one you'll see is like a little more ambiguous looking. Hope it's not too fast now. And let's make it 5 qubits. Oh, why did I just do that? Whew, brutal. Got that going. And incidentally, if you're wondering how I made all these cool diagrams,
Yeah, I am.
There's a little program called Tixit, which allows you to like lay out the nodes and the strings and kind of like bend them and stuff, and it'll generate LaTeX code for you.
Wow.
And this particular piece of software was like developed, I think, by like Alex Kissinger or whatever, who's a great guy. Like he collaborated with on a book called Picturing Quantum Processes. That's quite excellent and full of those, you know, amazing diagrams, which, you know, I think really breathe life into, you know, what normally is like algebra. Anyway, so like here's just like the last section. Just like these are just the final words, basically. So, you know, not all entangled black holes correspond to what we call semi-classical wormholes, even if they allow information transfer. Maybe next time we'll talk more about like how to interpret that stuff. We'll talk maybe next time more about the SYK model, which involves Majorana fermions and all this cool stuff. That is known to be dual to a conformal field theory, and like as such, you know, the whole ADS CFT thing works. And, you know, we can think about like a sort of geometrical interpretation here. We can like define a boost operator in terms of the Hamiltonian on the right minus Hamiltonian on the left, the time translation operator, like the energy operator, Hamiltonian on the left, Hamiltonian on the right, plus the coupling, minus like a little normalization kind of thing. And then interestingly, we can define these like, so these sort of like momenta looking operators. Sorry, there should be an equal sign there. And, you know, these generate null shifts. And the idea is like, you can use them, like instead of just like evolving, so I should say like, we can evolve the like wormhole step by step. We can also evolve it continuously in time. if we evolve it continuously in time, we can consider like different operators, like not just like the Hamiltonian itself. And specifically, we consider these sort of operators that act kind of like momenta, in the sense that they do, in fact, translate the thing through the wormhole. And there's a sort of argument here that if you look at, for an operator on the left, the amount of momentum that's sort of like inserted is proportional to the size, because you see here that, for P plus here, the Hamiltonian acts on the right, but the coupling is the part that acts on the left. And so for for P plus and P minus, the amount of momentum on the other side is proportional to the size. Anyway, I'm sorry, that was probably very confusing, but the point is that the message of this paper is that there's an intimate relationship between size and momentum. And this is like basically a quote from that paper. The size wave function, in other words, a sort of wave function organized by size, like we were talking about, like the Pauli basis. The size wave function of an operator O on one side is dual to the momentum space wave function of a particle created by O. And then finally, philosophically, it's worth just closing out on this note about black hole complementarity. This whole thing works because we've been saying, like, on the one hand, we have a picture where we throw a qubit in the left black hole, gets ever closer to the event horizon, gets scrambled over its surface. That's what we've been describing. And we like couple, and then this thing like unscrambles, right? That's literally what we have here, like qubits, scrambling, scramble, unscramble, But the idea is that, like, from the perspective of that qubit, if you were the one who fell into the black hole, you wouldn't experience anything unusual at the event horizon. You would just sail through it like it was empty space. You might not even know you're going through a wormhole, right? And there's this general principle that anytime there's a horizon, like an event horizon, the black hole, and you're wondering what states that are inaccessible to me lie behind that horizon, the principle is that those states that lie behind the horizon are dual to states that are on this side of the horizon. So in the case of the black hole, the idea is that the interior geometry of the black hole is dual to, for people who live on the outside, the event horizon and the Hawking radiation. They're actually the same quantum states, two different perspectives. And so in some sense, the interpretation of these Hilbert spaces is actually observer dependent if you buy into this idea of black hole complementarity. So in other words, I'm standing outside the black hole. And I'm wondering, what's the quantum state of the interior of the geometry of the black hole? And the idea is that, for me, it is just the quantum state of the Hawking radiation plus the state on the event horizon. Uh-oh, Marty's gone. Okay. Well, that basically concludes the discussion. Thank you for those of you who have remained. I see Andre, a certain Krishna, and Tim. And so
you'll tell us when you put it on YouTube, and you'll
I'll upload it tonight, and I'll have like a bunch of links to the GitHub on the paper. Yeah, thanks for coming out, guys. If there's any other questions, I'm happy to stick around for a second and answer. If not, I suppose we're done.
Hello, one question from my side. So these are what you are doing is a complete simulations, right?
What kind of simulations?
Sorry?
So, there are simulations. I'm sorry, I just didn't hear you. Say it again.
So what you show just now is a complete simulation in QTIP.
Yeah, totally.
Okay. But do you have any real-time experience with Rigetti or something with IBM? IBM One?
I haven't. I haven't used IBM's system, but I have used Rigetti's, and I plan to rewrite some of this code to run on their system. And for the next meeting, I'll have that.
Okay. And you have any experience with the tensor network?
Yeah, I mean, I would say my favorite tensor network library is QUIMB. I like this one, QUIMB. It's good for tensor contractions. I've had some trouble using it for like machine learning the tensors, but tensor networks is something I want to know much more about. I know some, but not nearly enough of the tricks.
Okay. I think you in the tensor network, how you are doing? It's a more the machine learning approach or something. You are doing an entanglement approach in a tensor network.
Yeah, I wish I was more expert at using the machine learning to kind of, like when there's a whole idea that like, okay, you choose one of these, perfect size winding, Hamiltonians or something, and you get your thermofield double state. And the question would be, could we train like a MIRA, like a multi-scale entanglement renormalization on SOTS? Do we train a tensor network that gives like that TFD state? And then we can talk about like how the geometry of this tensor network corresponds to maybe the geometry of the wormhole or something. And that involves, training the tensor network so that it reproduces a particular thermofield double state or whatever. And, I haven't myself done too much of that, but yeah, I'd love to do that.
Okay. Quite interesting. I think you have the good base knowledge. How much how much experience you have actually? It's in the learning platform. It's just a general question. How much experience you have in this platform? Learning plus experience. It's more than 10 years, maybe, no?
Well, I think I became interested in physics around 2012, 2013. I started out as a writer. I was a creative writer.
Okay.
Although I've been like a computer programmer since I was like 12 or whatever. So I always had that. So, when I started learning quantum physics, I most appreciated people who brought like a computational mindset to it because I found that much easier to understand. More subsequently, I've like taken some classes, but no, I don't have a PhD or anything. Like I'm not a part of academia. How about yourself? What's your background?
You're asking me. I'm actually the author for Awesome Quantum Machine Learning GitHub page. You know that one or?
No, send it to me. Yeah, send me a link.
Okay, so that's I'm actually an electronics communication engineer, and similar like you, I'm working as a computer engineer. But anyway, I'm mostly working on the quantum platform. That's a target. And,
it's an exciting time.
Sorry?
It's such an exciting time to be working on this stuff.
Yes, indeed. And I started around 5 years before the whole journey. Now it's going on. Now we are more interested on the tensor network. So I think, as you said, that is preparing a network where in a real tensor approach. That is a complex part. Tensor network theory.
What you mean, like the difference between training with real numbers versus complex numbers? I just thought this is a thing that came up a lot of the time when I was working with these things, like whether you're using TensorFlow or different things, like just sometimes.
No. TensorFlow is different. TensorFlow is it's a simple tool. There, that's for marketing purpose. My knowledge. But this is completely different. This is a real tensor network. This is no fake of a matrix or something. This is a real tensor implementation.
That's awesome. That's great.
It's not that much awesome. Maybe in the future.
If people could like think in terms of like tensors, in terms of multilinear algebra, like it would solve so much, you figure so many results that we're familiar with now would have been, it was possible to know them like 100 years ago. But unless you have the computers, you can kind of see these structures, and we're just able to, with such facility, manipulate things on the computer that I think it just allows us. Like the classic example is quantum teleportation. I mean, they only really published papers on that starting, I think, in the 90s. But it involves nothing more complicated than what was known in the 1930s.
Yes, indeed. True.
Well, it was great talking to you. I have to go because
yes. It's a nice time actually. You can see maybe in the next meeting.
Yeah, I'll keep you posted. Yeah, great to meet you. Thanks for coming.
Yes. Thanks for the presentation. Wonderful one.
Yeah, if Andre and Tim are still here, then sayonara, suckers. And adios.
See you. Bye.